Hey guys, sorry. This will be the last video. Had some technical difficulties earlier. Had to cut the video short. Here we go. Sorry about that. I think I got it figured out now. This is where we left off last time, which was trying to figure out a solution's pH if both of your cation and anion from your salt will hydrolyze. Try to figure out which one's stronger. Here's an example from your book, a chart you can reference if you're not quite sure what to do with these solutions. They'll tell you what their cations and anions will form and what their pHs will look like. Here's oxides for representative elements in their highest oxidation states. Here's a sodium oxide in water making a base. Here's a carbon dioxide in water making an acid. And so just be aware that this is important for understanding if the oxide is going to be basic, if the oxide is going to be acidic, or if the oxide is going to be amphoteric, which is of course being an acid or a base depending upon the situation. And so we can see a lot of our bases are on the left side, a lot of our acids are on the right side of the periodic table. So when you're asked questions about those, you can kind of hedge your bet using that information. And so here we have one with nitrogen and water forming this, I think, nitric acid, which would be, of course, acidic. So how do we define an acid? There are a few definitions. Arrhenius acids, you've probably learned those in Gen Chem, produce hydrogen ions in water, and Arrhenius bases produce OH minus ions in water. A Bronsted acid is a proton donor, and of course a Bronsted base is the proton acceptor. And now we get to Lewis. Lewis is accepting a pair of electrons, and the base can donate a pair of electrons. It's a little different than the ones we've seen before. It's kind of like all Bronsteds are Lewis, but not all Lewis are Bronsteds, kind of a thing. I hope I said that right. Yeah, I did. Okay, so here we have oxygen and hydrogen. Oxygen donates some electrons, and we form a bond, where hydrogen's the acid, and oxygen's the base, because, oxygen is accepting that hydrogen, and the hydrogen as, I guess you could say, the hydrogen donor. And then here we have one where nitrogen and hydrogen form a bond to form NH4. And so hydrogen accepted that pair of electrons and makes it the acid. Nitrogen donated that pair of electrons, makes it the base. And so here we have one that's kind of cool because this is an acid-base reaction that really doesn't fit the Arrhenius definitions or the Bronsted-Lowry definition of acid-base, but it does change pH of solutions. And so we have boron trifluoride, which is normally pretty content with 6, and our NH3 ammonia ion and nitrogen is actually going to form kind of this coordinate covalent bond where it donates both of its electrons to boron. And so we end up creating this molecule here. And boron is accepting those electron pairs, makes him the acid. Ammonia is the base because it donates those electron pairs. And no protons, no hydrogen ions were actually exchanged, so it doesn't fit any other definitions. It's kind of useful for that. So, chemistry in action for acids and bases. What do we always talk about? Antacids and stomach pH, right? People get acid reflux, and of course, stomach acid is hydrochloric, and it's very acidic, and it burns the esophagus and things of that nature. So folks who have, stomach acid causing them troubles, they can take all sorts of things. Here's the common names: Alka-Seltzers, milk and magnesia, Rolaids, and Tums are some you're probably most familiar with. There's also buffered aspirin and the appropriate name Bufferin, which of course buffers acid-base changes. And here it tells you what's in them: calcium carbonate, sodium bicarbonate, aspirin, magnesium hydroxide, all sorts of things. A lot of carbonates, you'll notice. And so here we have magnesium hydroxide, the milk and magnesia, with the hydrochloric acid. Is a reaction that will make mag salt and water, magnesium chloride and water, and it's actually consuming some of that hydrochloric acid, so it's a little less acidic in your stomach. Here's a sodium bicarbonate making your regular old salt, regular old water, your regular old carbon dioxide, so it kind of fizzes a little bit in the water and stuff, but like an Alka-Seltzer would, but it's going to accomplish the job of kind of neutralizing a little bit of that stomach acid, and then it's all excreted on into the intestines, where the salt and the water really aren't going to cause any damage. So that's the application for acid-base chemistry. We'll start up next time, chapter 16, which is acid-base equilibria, so we'll be combining these two chapters. Thank you for your time. Sorry about the tech difficulties. I'll try to get those all worked out.